The next algorithm we're going to talk about is Shor's algorithm. We're going to spend the next 2 lectures talking about Shor's algorithm. I think Shor's algorithm is really important because, even though it was developed way back in 1996, in my opinion, it's still the most convincing example we have of the power of quantum computers. And it differs from the previous algorithms that we've seen in 2 respects. Okay, so we've already looked at the Deutsch-Josse algorithm, Bernstein-Vazirani algorithm, and Simon's algorithm. And all those algorithms we described in the oracle model, right? We assumed that we had access to a function f via a black box. Someone gives us an oracle to evaluate the function f. On the other hand, Shor's integer factoring algorithm, it works in the quantum circuit model. Okay, so we can really just design a quantum circuit. It can take as input an integer and output a factor of that integer. Okay, so we don't need to assume access to any black box or special oracle. Okay, so that's a really nice feature of Shor's algorithm. It works directly in the quantum circuit model. So a second difference is that the quantum algorithms that we've seen so far, they've kind of solved artificial problems, right? We're given oracle access to some function f, and we're promised that f has a special property. And a lot of times that property was kind of artificial, right? Like in the case of Deutsch-Josse, the promise was that the function was either balanced or constant. On the other hand, integer factoring, it's a real problem of practical importance. It's a problem that people are really interested in solving efficiently. And an efficient algorithm for integer factoring, it also breaks the RSA crypto system. Okay, so this is a problem that has real practical consequences if you're able to solve it efficiently. What is the integer factorization problem? In this problem, we're given an integer m, and we want to find its prime factorization. In other words, we want to write m as a product of powers of prime numbers. So in this problem, the input size is log m, right? Because that's the number of bits we need to represent m. Integer factorization is a problem that has been studied very intensely, classically, and the best known rigorous bound that we have is exponential in the square root of log m. On the other hand, Shor gives an algorithm whose running time is polynomial in log m. More specifically, it's about log m squared. Okay, so here I'm using this O tilde notation. So the tilde is used to hide factors smaller than log m. So there is an additional polynomial dependence on log m here. Okay, but roughly speaking, the running time of Shor's algorithm is around log m squared. Okay, so this is a pretty big gap here, right? Log m squared versus exponential of square root log m. But keep in mind that we don't know a classical lower bound. Okay, so a polynomial time classical algorithm for integer factorization could still exist. We don't know. Of course, that would be a huge development if someone were to find that. Okay, so let me kind of give an overview of what we're going to talk about in relation to Shor's algorithm. So the quantum heart of Shor's integer factoring algorithm is Shor's period finding algorithm. Okay, so this is really the quantum part of Shor's factoring algorithm. So integer factorization can be solved basically by solving this period finding problem plus some classical post-processing and some using some facts from number theory. Okay, so the first thing we're going to do is we're going to focus on Shor's period finding algorithm. Okay, and this is again going to be similar to the algorithms that we've already talked about, in the sense that the period finding problem we can again represent as an oracle problem. Okay, so we're going to be, given some function, we're going to be promised that that function is periodic in some sense, and we want to find the period of the function by making oracle calls to the function. Okay, so in this sense, it's very, very similar to Simon's algorithm. There, we're given a function. We are promised that that function was periodic over the group z2 to the n. So Shor's period finding problem is very similar, where we're given a function and we're promised that it's periodic, but just it's periodic over a different group. So it's going to be periodic over the group of integers modulo n. Okay. So in Simon's algorithm, we use the Fourier transform over z2 to the n, which is just the Hadamard transform. So to solve the period finding problem over the integers modulo n, we're going to develop the Fourier transform over the integers modulo n. So that's the first thing that we're going to do. We're going to motivate and introduce the Fourier transform over the integers modulo n. And next, then we'll actually see how to design an efficient quantum circuit for the Fourier transform over the integers modulo n. And then we'll also talk about some applications of the Fourier transform to phase estimation, which is a very important quantum algorithmic primitive that we'll see many times throughout the course. Okay, and once we solve the period finding problem, then in the next lecture we'll see how to combine this with some number theory, some classical post-processing to actually solve the integer factorization problem. So that's the plan for the next two lectures.